Welcome to the Data Engineering Primer. In this chapter, we're going to establish a strong foundation by understanding the role of data engineering and why it matters in modern cloud environments. To set the stage, let's start with a quick view of what we'll be covering. Now that we've introduced the chapter, let's take a quick look at what we'll be covering in this section. First, we'll make sure you clearly understand what data engineering is and why it has become such an essential discipline in modern organizations. From there, we'll explore how foundational technologies like Hadoop and Spark shape today's cloud data platforms and influence the way we design large-scale systems. We'll also clarify the role of the data engineer and how it differs from and connects with related roles such as data analysts, data scientists, and DevOps engineers. Next, we'll review the major building blocks of big data, including key concepts, data types, and the core architectures that support analytics and machine learning. And finally, we'll connect all these ideas to the AWS services and pipelines you'll use in real-world scenarios, giving you the complete context you need moving forward. With that overview in mind, let's move into the first major topic. Now that we've outlined what this session will cover, let's start with the most fundamental question. What exactly is data engineering? At its core, data engineering focuses on designing, building, and maintaining the data infrastructure that powers analytics, business intelligence, and AI or machine learning applications. A large part of the role involves collecting data from many different sources, whether it's databases, logs, APIs, or real-time streams, and transforming that raw information into something clean, structured, and usable at scale. And just as importantly, data engineers ensure that the data flowing through these systems remains reliable, timely, and easily accessible to all downstream teams, including analysts, data scientists, and decision-makers. Understanding this foundation sets the stage for exploring how the field has evolved over time, which is where we'll go next. As we understand what data engineering is, it's also helpful to see how the field has evolved over time. In the early days, data engineering revolved around traditional on-premises ETL pipelines feeding classic data warehouses. The process was heavily batch-oriented, and infrastructure was fixed, rigid, and difficult to scale as data grew. But as organizations began dealing with larger volumes of data and more complex use cases, these older architectures quickly hit their limits. This shift pushed the industry toward cloud platforms, distributed systems, and big data frameworks like Hadoop and Spark, technologies that made large-scale, parallel processing far more accessible. Today, modern data engineering emphasizes scalable cloud infrastructures, real-time streaming, data lakes, and automation using infrastructure as code. Governance and compliance have also become core responsibilities as data grows across multiple systems. With this historical evolution in mind, we can now look more closely at what the modern data engineer actually does in today's cloud-first environments. Now that we've seen how data engineering has evolved into a cloud-first, highly scalable discipline, let's take a closer look at what the modern data engineer is responsible for today. A data engineer owns the entire lifecycle of data, starting from how data is ingested to how it's transformed, stored, secured, and finally served to downstream teams. This end-to-end ownership ensures that data remains consistent and reliable across every stage of the pipeline. They are also responsible for designing architectures that are not just functional, but scalable, resilient, and cost-efficient, especially in cloud environments where workloads fluctuate and efficiency directly impacts cost. Beyond building pipelines, data engineers implement controls for data quality, lineage, and governance, ensuring that the right data is delivered to the right people with full compliance and transparency. And because data touches every part of the business, data engineers collaborate closely with BI teams, data scientists, and business stakeholders to support analytics, reporting, and machine learning initiatives. With this role in mind, we can now explore how these responsibilities enable analytics and AI across an organization. Now that we've outlined the key responsibilities of a data engineer, let's look at how those responsibilities directly empower analytics and AI across an organization. One of the most important contributions is preparing curated, well-structured datasets that feed BI dashboards and reporting tools. These curated layers make insights accurate, consistent, and easy for business teams to consume. Data engineers also ensure that machine learning teams have access to high-quality, reliable training data. Without clean and consistent data, even the most sophisticated ML models will produce weak or unstable results. Beyond batch analytics, data engineers design and build streaming pipelines that support low-latency, event-driven use cases, things like real-time monitoring, fraud detection, and personalized recommendations. And ultimately, all of this engineering work has one goal: transforming raw, unorganized data into actionable business insight. With this understanding, we can now step back and see how the data engineer fits alongside other related roles in the broader data ecosystem. Now that we've seen how data engineering powers analytics and AI, it's helpful to understand how the data engineer fits into the broader ecosystem of data and cloud roles. Each role supports a different part of the pipeline, but they all rely on each other. The data engineer is responsible for building the pipelines, storage layers, and governance controls that make reliable data available across the organization. Data scientists then use that curated, well-prepared data to develop predictive models and machine learning solutions. On the analytics side, data analysts use the cleaned and structured datasets to answer business questions, create dashboards, and support day-to-day decision-making. DevOps engineers play a key role as well by providing CI/CD, infrastructure as code, and platform automation that help data systems scale reliably. And ultimately, the business stakeholders are the ones consuming these insights to guide strategy and make informed decisions. With this ecosystem in mind, we can now transition into the next major topic, the foundation of all this work: understanding big data. Now that we've seen how different data roles work together, let's shift our focus to the data itself, and specifically, why modern organizations need more advanced systems to manage it. Big data refers to data sets that are simply too large, too complex, or too fast-moving for traditional systems to handle effectively. These workloads break the assumptions that older architectures were built on. Big data isn't limited to neat, structured tables. It includes semi-structured formats like JSON and logs, as well as fully unstructured data, everything from images and audio to documents and clickstream events. Because of this scale and diversity, big data requires distributed storage and scalable processing frameworks that can handle petabytes of information and high-velocity streams. To better understand these challenges, let's break big data down using the well-known 5 V's. Now that we understand what big data is at a high level, let's break it down using the classic framework known as the 5 V's. These help us see why traditional systems struggle and why modern architectures are necessary. The first V is volume, referring to the massive scale of today's datasets, from terabytes to petabytes, often coming from dozens or even hundreds of sources. Next is velocity, which speaks to the speed at which data is generated and needs to be processed. Real-time applications, IoT devices, and clickstream events all push data through systems at high speed. The third V is variety. Data no longer fits neatly into structured tables. It now spans logs, JSON, images, video, IoT signals, and much more. The fourth V is veracity, which focuses on data quality, consistency, and trustworthiness at large scale. The more data you have, the harder it becomes to ensure accuracy. And finally, value reminds us that big data isn't important just because it's big. It's valuable only when it leads to meaningful business outcomes that justify the investment. With the 5 V's in place, let's now explore why older systems struggled under these demands. Now that we've broken down big data using the 5 V's, it becomes much easier to see why traditional systems started to struggle. Older architectures were built around vertical scaling, meaning you would add more CPU, more memory, or bigger hardware to keep up. But this approach is both expensive and limited. You eventually hit physical and financial boundaries. Traditional ETL processes were also heavily batch-oriented, which made them too slow to support real-time analytics or high-throughput workloads that modern applications require. These systems relied on rigid schemas, which made it difficult to handle diverse or constantly evolving data structures like logs, IoT signals, or semi-structured formats such as JSON. And perhaps most importantly, traditional systems were never designed to handle unstructured data or low-latency use cases, making it extremely challenging to manage images, video, streaming data, or event-driven pipelines. All of these limitations created the need for new architectures and frameworks, which leads us naturally into how big data systems address these challenges. Building on those limitations, we can now clearly see the contrast between traditional data systems and modern big data platforms. Traditional environments typically operate at gigabyte to terabyte scale, rely heavily on batch ETL, run on on-premises hardware, and follow schema on-write models that require data to fit rigid structures before it can be stored. Big data systems, by comparison, are designed for terabyte to petabyte plus size and make distributed compute the default. They embrace cloud-native architectures that can grow or shrink as workloads change. Instead of vertical scaling, big data platforms rely on horizontal scaling, spreading storage and compute across clusters and managed cloud services. This allows the system to handle massive datasets, higher throughput, and more complex use cases. And across all of these improvements, big data systems focus heavily on performance, elasticity, and fault tolerance, ensuring that large-scale data workloads remain fast, cost-efficient, and highly resilient. With this modern foundation in place, we can now explore the real-world use cases that make big data so impactful. Now that we've compared traditional and big data systems, it becomes much clearer why organizations invest heavily in modern data platforms. These capabilities unlock a wide range of high-impact use cases. One of the most common is real-time monitoring and analytics dashboards, where businesses track system health, operations, and customer activity with just a few seconds of delay. Another major use case is customer personalization and recommendation engines. These systems analyze large amounts of behavioral data to deliver tailored product suggestions, personalized content, and targeted experiences. Big data platforms also enable fraud and anomaly detection at scale, allowing organizations to identify unusual patterns across billions of events with very low latency. And finally, industries that rely on devices and sensors, such as manufacturing, transportation, and energy, depend on big data for IoT telemetry, sensor analytics, and predictive maintenance, helping them reduce downtime and optimize performance. These examples illustrate how big data systems deliver real business value. Next, let's explore the ecosystem of technologies that make these use cases possible. Now that we've seen the major use cases powered by big data, it's helpful to understand the technologies that made these capabilities possible. Two of the most influential components of the modern data ecosystem are Hadoop and Spark. Hadoop introduced the idea of distributed storage through HDFS and parallel processing using the MapReduce model. These innovations made it possible to store and analyze massive datasets across clusters of low-cost machines, something that was simply not practical with traditional architectures. As workloads grew more complex, Spark emerged as a faster and more flexible alternative. It delivered in-memory processing, support for SQL, streaming, and machine learning, and a unified programming model that significantly improved performance over MapReduce. Together, Hadoop and Spark established the core patterns that underpin most of today's cloud data platforms, including AWS services that build on these same distributed and scalable principles. With this ecosystem in mind, we can now take a closer look at Hadoop itself and how its architecture shaped big data engineering. Since Hadoop played such a significant role in shaping the modern big data landscape, let's take a closer look at its core components and why they mattered. Hadoop began with HDFS, a distributed and replicated file system that stored data across many machines. This allowed organizations to keep extremely large datasets reliably, even if individual nodes failed. On top of that storage layer, MapReduce provided a way to process data in parallel using a batch-oriented approach. While powerful for its time, MapReduce relied heavily on disk operations, which made it slower compared to modern in-memory engines. Hadoop also introduced Yarn, a cluster resource manager that enabled multiple compute engines to run on the same cluster, improving efficiency and flexibility. Even though Hadoop itself has faded in popularity, These foundational patterns continue to influence today's cloud architectures. Concepts like distributed storage and parallel processing directly shaped S3-based data lakes and services like Amazon EMR. With this understanding of Hadoop's foundation, let's move on to why the industry eventually moved toward faster, more flexible engines like Apache Spark. Now that we've looked at Hadoop's core building blocks, it's important to understand why the industry gradually moved away from Hadoop-based systems. One of the biggest challenges was the high operational burden of running Hadoop clusters on-premises. Teams had to manage hardware, networking, scaling, and constant tuning, which made these environments expensive and complex to maintain. Beyond that, Hadoop offered limited support for real-time or interactive workloads. Most processing was batch-oriented, meaning results came minutes or hours later, not ideal for modern analytics or streaming needs. Another major limitation was that MapReduce was heavily disk-bound and slow for many use cases. As data volumes exploded and workloads became more dynamic, organizations needed engines that could operate in memory and deliver much faster performance. With the rise of the cloud, Spark-based and cloud-native architectures became far more flexible, easier to scale, and significantly faster to adopt. These modern platforms kept the good ideas from Hadoop, but removed the operational pain that held Hadoop back. And this shift is what led to today's data lake and distributed compute models on AWS and other cloud platforms. After understanding why Hadoop gradually declined, it's easy to see why Apache Spark emerged as the modern engine of choice. Spark was designed to overcome the limitations of disk-bound MapReduce by introducing in-memory, DAG-based distributed processing, which dramatically accelerates computation. Spark also brings a unified engine that supports batch workloads, streaming analytics, SQL processing, machine learning, and even graph computation, all within the same platform. This versatility makes Spark far more flexible than traditional Hadoop approaches. At the core of Spark's usability are DataFrames, RDDs, and its lazy evaluation model, which optimize execution plans and make large-scale processing both efficient and developer-friendly. Because of these strengths, Spark is exceptionally well-suited for ETL pipelines, feature engineering, and machine learning at scale, which is why it powers many of today's cloud-native data platforms, including those on AWS. Spark truly represents the next generation of distributed data processing. Now that we've seen why Spark has become the modern distributed engine, let's look at some of the key libraries that make it so powerful, and how these capabilities integrate directly with AWS. Spark provides Spark SQL and DataFrames, which bring a structured SQL-like interface to big data processing. This makes querying large datasets intuitive and highly optimized. For workloads that need responsiveness, Spark's structured streaming enables near real-time data pipelines, supporting use cases like live dashboards, anomaly detection, and continuous ETL. Spark also includes MLlib, its built-in distributed machine learning library. While more advanced ML often uses frameworks like TensorFlow or PyTorch, MLlib remains a strong option for large-scale classical algorithms such as clustering, regression, and recommendations. All of these capabilities integrate tightly with AWS. Spark runs natively on Amazon EMR, and Spark engines also power AWS Glue for serverless ETL and Athena Spark for interactive, notebook-based analytics. Together, Spark's libraries and AWS services create a unified environment for scalable ETL, streaming analytics, and machine learning. As we move from the tools and platforms into the day-to-day realities of the role, it's important to understand what a data engineer is actually responsible for. At the core, everything centers around building systems that make data usable, reliable, and scalable. A data engineer begins by designing and maintaining scalable, resilient data pipelines that can handle growing volumes of data without breaking under pressure. From there, the work expands into ingesting, cleaning, transforming, and enriching raw data. This is where messy data from many sources is shaped into something analytics-ready. Another critical responsibility is ensuring reliability, lineage, and governance. That means tracking where data comes from, maintaining quality, and enforcing policies and controls that keep data compliant and trustworthy. data engineers also focus heavily on performance and cost optimization, examining where pipelines can run faster, more efficiently, or more economically, especially in cloud environments. Finally, modern data engineering involves a strong DevOps mindset, automating deployment, testing, and monitoring so pipelines run consistently and recover quickly from failures. Together, these responsibilities define the foundation of a successful, high-impact data engineering practice. Now that we understand the core responsibilities of a data engineer, let's place those responsibilities within the broader data lifecycle, specifically how it plays out in the cloud. Every modern data platform follows a similar set of stages. AWS provides purpose-built services for each one. We begin with ingestion, which can happen through batch uploads, real-time streaming, APIs, or third-party connectors. This is where data first enters the ecosystem. Next, we store that data using services like Amazon S3, Redshift, or DynamoDB, all governed centrally through lake formation to ensure consistency, governance, and access control across the data lake and data warehouse. From there, we process the data. This may involve ETL or ELT workflows powered by EMR, Glue, or serverless compute with Lambda. This is where raw data is cleaned, transformed, and prepared for analytics or machine learning. Once processed, the data is ready for analysis. Services like Athena, Redshift, QuickSight, and SageMaker enable interactive queries, dashboards, and predictive modeling, all on top of the same governed data. Finally, we secure and govern every layer using IAM for access management, KMS for encryption, CloudTrail for auditing, and lake formation for centralized governance. Together, these stages form the complete data lifecycle in the cloud, and they define how data engineers design, operate, and optimize modern data platforms. As we walk through the data lifecycle, it's important to recognize that not all data looks the same. Different types of data influence how we store it, how we process it, and which tools we choose on AWS. First, we have structured data. This is the most familiar form, organized into fixed schemas such as CSV files, SQL tables, or Excel spreadsheets. It's clean, tabular, and easy to query. Next is unstructured data, which is free-form and doesn't fit neatly into rows and columns. This includes text documents, images, audio files, and videos. Organizations generate massive volumes of this type of data, and it often requires specialized processing techniques. Between the two is semi-structured data. This includes formats like JSON, XML, logs, or email headers, data that has some structure but not a rigid schema. Modern analytics platforms, including AWS services, are designed to handle these formats efficiently. Finally, the distinction between tabular and hierarchical data shapes our storage decisions. Tabular data often fits well in databases and warehouses, while hierarchical formats like JSON or logs align more naturally with data lakes. Understanding these data types helps determine the right architecture, the right tools, and the right processing strategies in a modern cloud environment. Now that we understand the different types of data, let's look at where this data actually comes from and how it's typically stored. In most modern architectures, data enters the system from a variety of sources: traditional databases, application logs, third-party APIs, and increasingly from real-time streaming platforms such as Kinesis or Kafka. Each of these sources delivers data with different characteristics and levels of structure. A large portion of raw data arrives in familiar text or row-based formats like CSV, Excel, JSON, or XML. These are easy to work with and widely supported, but they're not always the most efficient for large-scale analytics. For big data workloads, binary and columnar formats are far more efficient. Formats such as Parquet, Avro, ORC, and Feather enable faster queries, better compression, and reduced storage costs. These are the backbone of modern data lakes and analytics pipelines. And for highly structured, query-intensive workloads, we still rely heavily on SQL tables. Traditional relational databases and data warehouses remain the best choice when performance, constraints, and strong consistency are important. Understanding these formats and when to use each one is essential for designing scalable, high-performance data engineering solutions. Now that we've looked at the different sources and formats data can arrive in, the next step is understanding the characteristics that define big data in practice. This brings us to the classic 3 V's of data, a simple but powerful framework used across analytics and data engineering. The first V is volume, which represents the total amount of data an organization must manage. As businesses scale, even routine operations can generate terabytes or petabytes of information, influencing how we store, secure, and process it. Next is velocity, the speed at which data is generated and needs to be processed. With real-time applications, like streaming logs, IoT sensors, and live customer interactions, data doesn't just come in large amounts, it comes fast. The third V is variety, reflecting the diversity of data structures and formats we deal with. From structured tables to JSON logs, images, and audio, data engineering solutions must accommodate all of these formats efficiently. Together, these 3 V's shape the decisions we make about tools, storage systems, compute engines, and the overall architecture of our pipelines. Understanding them helps us design systems that are scalable, reliable, and aligned with business needs. Now that we understand how data volume, velocity, and variety shape our technical decisions, the next question becomes, where should all of this data live, and how should it be organized? This leads us into the core data models and storage architectures that power modern analytics platforms. We start with the distinction between relational databases and NoSQL systems. Relational databases enforce strict schemas and are ideal for transactional workloads, while NoSQL models, such as document stores, key-value pairs, and graph databases, offer flexibility for semi-structured and rapidly evolving datasets. For analytical environments, we also look at dimensional modeling, particularly star and snowflake schemas. These structures shape how warehouses organize facts and dimensions to optimize reporting and aggregation performance. At a higher architectural level, organizations rely on data warehouses, data lakes, and increasingly, lakehouses. Warehouses excel with structured, curated data. Lakes provide scalable storage for raw, diverse formats, and lakehouses blend both worlds to support advanced analytics and machine learning. Finally, a key design choice is whether we adopt schema on-write or schema on-read. Schema on-write enforces structure before data is stored, while schema on-read applies structure only when data is queried, offering more agility for big data use cases. Together, these models define how data flows, how it's organized, and how efficiently it can be used across analytics and machine learning workloads. As we shift from how data is modeled and stored, the next piece of the puzzle is understanding the compute and storage foundations that make those architectures actually work at scale. In the cloud, one of the biggest decisions is choosing between serverless compute, such as Lambda, AWS Glue, and Athena, and provisioned compute options like EMR clusters or EC2. Serverless services automatically scale and remove operational overhead, while provisioned systems give you more control for large, long-running workloads. Storage also plays a major role. AWS S3 offers multiple performance and cost tiers: hot, warm, cold, and archival, allowing you to optimize how frequently data is accessed and how much you spend to store it. To support large datasets and fast queries, data engineers rely on partitioning, bucketing, and sharding. These techniques split data into manageable units, improving parallelism, reducing scan times, and enabling predictable scalability across compute engines like Spark, Athena, and Redshift. Finally, S3 lifecycle policies help balance performance and cost automatically. They move data to cheaper tiers over time, ensuring the system remains efficient without manual intervention. Together, these compute and storage fundamentals form the backbone of a reliable, scalable cloud data platform, setting the stage for the pipelines and processing patterns we'll explore next. Now that we've covered the foundational compute and storage layers, let's look at how data actually flows through a modern analytics environment. This brings us to ETL and ELT pipelines, the core engines that move and prepare data across the platform. These workflows always begin with extract, which focuses on reliably pulling data from source systems. That can include APIs, databases, SaaS platforms, logs, or streaming sources, and the key goal is to capture data consistently and without loss. Next comes transform, where raw data is cleansed, standardized, enriched, and secured. This is where business logic is applied, where missing values are addressed, formats are aligned, and sensitive information is masked or governed. Finally, the load stage delivers the processed data into the right destinations, whether that's a data lake, a warehouse like Redshift, or downstream data marts that fuel BI dashboards and ML pipelines. Because these steps often involve dependencies and multiple systems, data engineers rely on orchestration tools to coordinate everything. Platforms like AWS Step Functions, Glue Workflows, or Airflow make sure each task runs in the right order, retries when needed, and tracks lineage for observability. Together, ETL and ELT pipelines form the operational backbone of any data platform, turning raw data into trusted, analytics-ready assets. Now that we've explored how ETL and ELT pipelines function conceptually, let's look at the AWS services that bring those workflows to life in the cloud. Starting with AWS Glue, this is AWS's serverless Spark-based ETL service. It not only lets you run distributed data transformations without managing clusters, but it also provides a managed metadata catalog, which becomes a central source of truth for schema discovery and table management across your data platform. Next is AWS Lambda, which plays a key role in event-driven transformations. Lambda is ideal for lightweight processing, enrichment, validation, or glue logic that triggers whenever new files land in S3 or data arrives through an event stream. For larger-scale compute, Amazon EMR provides managed big data clusters optimized for Spark, Hive, Presto, and other analytics frameworks. It gives you far more control over scaling, performance tuning, and distributed workloads when Glue isn't enough or when custom configurations are required. To coordinate everything end-to-end, AWS provides powerful orchestration services like Step Functions, EventBridge, and MWA for managed Apache Airflow. These tools tie multiple steps together, handle dependencies, enable retries, and manage schedules, ensuring your pipelines run reliably and transparently. Together, these services form the backbone of modern, cloud-native ETL pipelines on AWS, scalable, automated, and designed for both batch and real-time data movement. Now that we've looked at the core ETL and orchestration services, let's zoom out and see the broader ecosystem of AWS tools that form the foundation of modern data engineering. We start with storage because every data pipeline begins with where data lives. Amazon S3 acts as the central data lake for raw, curated, and processed datasets. Redshift provides high-performance analytical storage, while RDS and DynamoDB support operational workloads and structured or key-value data needs. Next is processing, where data is transformed and prepared. AWS offers multiple engines depending on scale and complexity. Glue for serverless, Spark ETL, EMR for customizable big data clusters, and Lambda for lightweight event-driven processing. To coordinate everything end-to-end, AWS provides a suite of orchestration tools. Step Functions handles workflow logic and retries, EventBridge manages event-driven triggers and schedules, and MWAA brings fully managed Apache Airflow for more advanced DAG-based orchestration. Once data is ready for analysis, AWS offers powerful querying and BI tools. Athena enables serverless SQL directly on S3. Redshift Spectrum extends Redshift queries into your data lake, and QuickSight delivers dashboards and visualizations for business users. And running beneath all of this is security and governance, which ensures data integrity, protection, and compliance. IAM controls permissions, KMS secures data with encryption, Lakeformation manages lake-wide governance, and CloudTrail provides full audit logging across the environment. Together, these services create a complete, end-to-end data engineering platform on AWS, from ingestion and transformation to analytics, orchestration, and governance. As organizations scale their data platforms, It's not enough to simply ingest and store data. You must ensure that the data is trustworthy, well-documented, and compliant with regulations. This is where data quality, metadata, and governance come into play. We begin with data quality dimensions, which include completeness, accuracy, and consistency. These are the foundational checks that determine whether data can be relied on for analytics, machine learning, or business decision-making. Next, we have schema evolution and data versioning. As business requirements change, data structures evolve. New fields get added, old ones become obsolete, and formats shift. A robust data engineering system must handle these changes gracefully without breaking pipelines downstream. To provide structure and discoverability, we rely on metadata and data catalogs. On AWS, this is typically powered by the AWS Glue data catalog, which tracks table definitions, schemas, partitions, and helps unify how data is referenced across services like Athena, EMR, and Redshift. Finally, governance includes lineage, auditing, and regulatory compliance. Whether you're dealing with GDPR, HIPAA, or internal audit requirements, you need visibility into where data came from, how it was transformed, and who accessed it. These practices help maintain trust, meet legal obligations, and keep the entire data lifecycle secure and transparent. Together, these components ensure that data is not only available, but also accurate, governed, and ready for reliable use across the organization. In modern data engineering, a handful of architectural patterns show up again and again because they solve fundamental challenges around scale, latency, and flexibility. Let's walk through some of the most important ones. We start with ETL versus ELT, which defines where transformation happens. Warehouses like Redshift typically favor ELT, loading raw data first, then transforming it inside the warehouse for better performance. Data lakes, on the other hand, often lean toward ETL, where data is cleaned and prepared before landing in storage to maintain structure and reliability. Next is the Lambda architecture, a hybrid design that merges batch processing with real-time streaming. Batch provides complete and accurate data, while streaming delivers low-latency insights. Together, they offer both speed and correctness in analytical systems. Another widely used pattern is fan-in and fan-out. Fan-out distributes data across multiple consumers for parallel processing, while fan-in aggregates data from many sources into a single downstream workflow. These patterns are essential for streaming pipelines, microservices, and large-scale distributed systems. Workflow coordination is handled through workflow chaining, using tools like AWS Step Functions or Apache Airflow. These orchestration systems help manage dependencies, retries, error handling, and multi-step pipeline execution. Finally, there's the decision between schema on read and schema on write. Schema on write enforces structure up front, which is ideal for warehouses and BI workloads. Schema on read defers structure until query time, making it more flexible and better suited for semi-structured or exploratory workloads in data lakes. Together, these patterns form the backbone of scalable, reliable, and modern data engineering architectures. As we wrap up the foundational concepts and patterns, it's helpful to look at how these ideas show up in real-world data engineering projects. These examples illustrate the kinds of problems organizations solve every day using the tools, architectures, and workflows we've been discussing. One common scenario is building real-time customer behavior dashboards. These solutions often combine streaming ingestion, stateful processing, and interactive analytics to help businesses react instantly to user activity, transactions, or operational events. Another major use case is migrating on-prem Hadoop workloads to Amazon EMR. Organizations move to EMR to reduce operational overhead, scale more efficiently, and integrate tightly with cloud-native services like S3, Glue, and Lake Formation. This type of migration often involves refactoring existing Spark, Hive, or Presto workloads to run more efficiently in the cloud. A third scenario is building a governed S3-based enterprise data lake. This includes designing ingestion pipelines, creating metadata catalogs, enforcing access controls, and setting up lifecycle policies, all to ensure that data is secure, discoverable, and analytics ready. We also see federated querying across S3, Redshift, RDS, and DynamoDB becoming increasingly popular. Services like Redshift, Spectrum, and Athena make it possible to query multiple storage systems without moving the data, enabling unified analytics across diverse sources. Finally, real-world data engineering requires automated deployment, testing, and monitoring of pipelines. Using CI/CD, infrastructure as code, and observability tools ensures that pipelines remain reliable, scalable, and easy to update as business needs evolve. Together, these scenarios highlight how data engineering principles translate into practical, high-impact solutions across different industries.